Okay. So again, this is a brief discussion on macroscopic transport. So basically, it's a relatively short lecture on macroscopic momentum transport overall. We have dealt with friction factors, and we will actually use how to see how to use them in a larger system. But that is the only thing that is basically in between us and moving on to heat and mass transport. So this is sort of the bulk of the most difficult part of the transport class. A lot of other classes actually start with, especially when it's an introduction, they start with heat and mass transport because they're actually somewhat easier to develop. In particular, because they're looking at temperature fields, for instance, and temperature field is a scalar field as opposed to velocity field. Okay? Velocity field is a vector field, so then we have to deal with the stress tensors and the concepts that are typically more difficult to deal with. But since this is a graduate class, we're actually starting from momentum transport because it's typically the first one we have to deal with anyway. So in any event, we're gonna either today or on Wednesday, depending on how fast we finish today's lecture, we will actually start with heat transport. Now, regardless of the type of transport, and this is sort of the reason why this class is taught with all of the types of transport together, is that you can actually see the similarity. So there is molecular basis for viscosity, molecular basis for... So for all of the transport coefficients, we can look into their origin on the molecular scale. So in each of them, we briefly introduce the molecular basis for the transport coefficient. In momentum, that was viscosity. We will have parallel coefficients in energy and mass transport. And then we're going to do shell balances. So you should by now kind of be really familiar with the procedure and just jump right in and equations of change. So you can see, again, parallels in all of these types of transport in the way we solve the problems. So the worst you have already seen. From now on, it should be the easy ride. Okay. All right. So quick review. So on microscopic scale, we have equations of continuity and motion. That should be very familiar. And then mechanical energy equation we get by basically doing a dot product with velocity of this vector equation. So it's a vector equation, so if when I do a dot product, I'm going to get a scalar equation. And with some rearrangement, one can actually see that there's here quite a soup of vector and scalar quantities that are interacting with each other. So we did this practice. So can you still remember how they're matched together by system of elimination? Okay. So the change of this is kinetic energy. Okay. So then I have where is the work done by viscous forces? Must be something with tau. Related to the viscous forces, we also have friction loss, which is right here. And this operator, this is a tensor or a matrix, and this is a tensor or a matrix. So this is sum of tau ij times whatever is ij element of this matrix. That's dvi dxj, right? So basically tau ij times whatever is that. So for two matrices, I can get, it's a scalar is the result. So I take all of the corresponding elements, multiply them, and then sum all of those multiplications together. So that is actually friction loss right here. So that might be something that you're not necessarily familiar with as an operation. And then we have work done by pressure. Yes?
I thought that the last Friday mentioned the friction loss is the second in the middle one in the last row. Is the friction loss?
That's what I've been showing now. Oh, okay.
That one.
Yes, that's what it is. Now, there might be, I'm looking at this screen, it seems that there is a lag. Okay, so I need to actually monitor here. Yes, that is the one, and that's what I thought I was showing. Okay, but it seems that it's a little slow for some reason. Okay, this one, yes.
Okay.
So, this is the work done by viscous forces, this is the friction loss. All right, now what we have is, if we're going to go with a method of elimination, it is relatively easy to spot convection. Okay, and what is added by convection? We actually see, so we're looking at the change of kinetic energy. This is kinetic energy as well, and it's literally whatever flows in, right? So this is our familiar term with convection, and this divergence operator, it basically collects what goes in normally through the boundaries, right? So if I have a control volume and that control volume has a surface as a boundary, then whatever is normal to that surface, that's essentially what divergence operator collects. There is a theorem that relates divergence and surface integrals, okay? And that's where it comes from. So physically, that is typically what divergence does. So we have, this is addition by convection. We have work done by external forces that is easy to recognize. And then I have two terms that are left. One is work done by pressure, okay? And then another is reversible conversion of kinetic to internal energy. So this is essentially the reversible conversion of kinetic to internal energy. It's related, so if I have incompressible fluids, then this is actually going to be zero, right? But compressible fluids, you can imagine that it can basically store energy by compression. So that is this reversible conversion, and this is the work done by pressure. This is a PV term that we are typically used to in fluids. Okay. Now, to get the to get to the larger scale, we typically have to integrate over the entire system. So I can take all of these equations and integrate them to get the balance. So I take volume of interest and integrate. And typically, if I have a system that is relatively close, then mass and momentum balance are relatively simpler because typically I have one or two ins and outs that I control inside of the system, and the rest should be insulated. Now, with the mechanical energy, it's a little, the situation is a little more difficult because there is always some internal loss that it's extremely hard to account for. And this part of this lecture is basically to estimate these losses. Okay. So here's an example system. So I typically, just in terms of notation, I take a U1 and U2 as identity vectors that are orthogonal to the inlet and outlet. So those are my only inlets and outlets. There is no other exchange through any of the other boundaries. And I have some average velocities along those planes. So my velocity term is basically this average velocity times the identity vector. And this I can do for both boundaries. Okay? And then I have average mass rate of flow, which is W, which is rho times average velocity times surface area that is either inlet or outlet. Again, this term has either ones or twos here. Okay? And then the total mass in the system is integral of the density. Now, the mass balance is always simple. So my change of mass, nothing can go through any other boundaries. I don't have reactions that I'm accounting for. So basically whatever comes in and comes out through those two inlets, through inlet and outlet is it. So basically the change of mass is minus W2 minus W1. So I refer to this term as delta, in this case delta of W. So basically my d dt of total mass. Yeah, it gets even stuck a little bit. All right, I'm moving it. I'm moving. No? Okay. Well then, delta W, the one below the mouse, is the term that I'm pointing at. All right. Now, what about the momentum? So if I integrate momentum, it's basically my P total is integral of PV dV. Okay? And then the change of this is basically what comes in and out of the boundaries. Okay? And pressure work on the boundaries, the force of the solid areas that are exerted on the fluid, which is basically inverse of the fluid force on the boundaries of the system, and the work of the external forces. So basically, those are my four contributions. Now, this is a nice equation, but we also need to be able to compute something. And basically, there's often an approximation done. Essentially, I have rho. The problem is to estimate average of v squared. I can write it as w divided by average of v times v squared, and then this term becomes this one. Delta, again, is this difference between outlet minus inlet. But sometimes when I can't figure out what this is, I can approximate that this is equal to the average of V. Now, in reality, I know that I can't just interchange the two. So average of V squared is not the square of the average, because there are integrals involved underneath. Okay? So this is my momentum balance, just an alternative way to write it down. So I have the mass rate, so W, so that's rho average Vs, and then V squared V plus PSU. This is the force of the solids on the fluid, and the external forcing in G. All right. And again, this is the approximation that I mentioned. So when we can do this when we don't know how otherwise to estimate. Okay. At steady state, I'm going to have that basically this side is 0. So basically I can equate this and express the force on solids and fluids is the same as the negative fluids force of the fluid on the solid, and this is something that we can typically calculate from the equations. We have at least sort of part by part when I go through the system, pipe by pipe, if you will. Okay. So for flow in pipe, we will have that this force is a familiar one that we called Fk in friction factors. So this is difference between the pressures at the two ends times the area, cross-sectional area, R squared P. All right. So now if I wanted to also rewrite it this in the, so my goal is to actually look at the total energy and not just kinetic energy. Then I have to do a little bit of rearranging, and I'm not going to go through much details of this other than just kind of through the PowerPoint. Otherwise, it's a little bit of writing down. So this is my kinetic energy balance. Now I will basically rewrite this term in order to get the potential energy balance as well and throw it on this side. So to look at the change in both kinetic energy and potential energy. So here's how we do that. We take that term and we define potential energy per unit mass, which is such that G is the gradient of V. So basically I define this field so that I get the gravity as a minus gradient of this potential. Then a little bit of your favorite vector rearrangements. So I can rewrite this V dot G as V dot gradient of V. And then I know that this is the same as divergence of rho Vf minus divergence of rho V times F phi. And basically, if I apply equation of continuity, I can get that this is divergence of rho V, this capital phi, minus d rho dt phi. Okay? So this is the part that I was looking for. Since this is actually not dependent on time, I can do a derivative of it just fine and put it on the right hand side. Okay, and this is now my both kinetic energy and potential energy term. And here I have again divergence of both kinetic energy and potential energy term. So remember, this is the one that was added. Okay. So that term with gravity here has now made its way to the convective term, as well as the change of the potential energy. Okay. And again, I mentioned this already. So this is so-called friction loss or viscous dissipation term. It's always positive. You're always at a loss. So it is estimated for laminar flow in a tube, which we rarely have, but this is still a useful equation to use. It's mu dvzdr square if I have, again, flow in a tube. And I can actually, whenever I have two tensors, this is the way I get this quantity. So again, individual terms in corresponding ij position, and then I just sum them, all of them up over all rows and terms. Right. So are you dizzy yet from all of the the terms? All right, so where are we? So this is basically when I integrate it. Okay, then, so this was my differential equation version. Now I integrate to get the totals in my system. Right? So when I integrate to get the totals in the system, then I have total kinetic and total potential energy, sum them up, and the change in that energy, okay, is in change in what flows in. Again, in this system, things are just coming in and out of only through inlets and outlets. Okay? So this is basically the integration of those terms. Then I integrate the work of the pressure forces, work on fluid by pressures on the inlets and outlets. I have net change due to moving surfaces doing work on fluid. I have net change due to the compression and expansion within the system if I have compressible fluids. And I have the rate of decrease in energy due to viscous dissipation. And this is the major loss term. If anybody's writing down, I can wait. Otherwise, I'll just keep flashing big equations at you, and we're going to do an example at the end to do this. And of course, I will ask you to, recall all of these equations term by term. If I wake you up at 2 a.m., you should know what terms are. You should do that matching at the beginning, and by method of elimination, figure out which term is what. That you should definitely know. All right. So at unsteady state, okay, we will have the following terms. So this is my favorite term, delta. Delta is basically outlet minus inlet versions of potential energy, P divided by rho. Remember, this is W is rho Vs. So this is the short way to write this equation. And actually, so this should vaguely remind you of this. Does anybody recall this equation? Bernoulli. There you go. So it should be relatively easy to remember how to write down. Okay. So at steady state for Bernoulli equation, basically we were ignoring all of the losses we could possibly have. Okay, so in Bernoulli equation, so all of these were essentially zero, okay, except that they're not. All right, so if I divide by W and approximate this term, so in order to compute this, we approximate the following terms of this one. Right here, my mouse is slow as if it were a Monday morning or something. All right, so this and this, I combine them together, and they can be approximated as an integral of 1 over rho dp. And this gives me an equation that we work with. So basically, I have interconversion of kinetic energy, potential energy, and enthalpy, which is on the left-hand side, and it's equal to the work done on fluid by moving parts, which is this one, minus friction losses. All right. So in order to estimate all of these, I take so-called friction loss factor, EV, and this is a factor that is based on both the geometrical shape and the Reynolds number, and there's a lot of data that is simply a lot of measured data, so one goes to tables to estimate this term. And for instance, you will get for a straight tube, there's table which is 751, which will estimate, it will take friction factor for the tube, hydraulic radius, and the length of the tube. Okay. So this is where we're putting all of the individual friction factors that we work with. So we had friction factor for flow through the tube, which is most common part of any larger system. Then we had flow around the sphere and the sphere packs. So those can be used to basically estimate friction losses in a larger system. The way we will have to work with those is to actually look at the system as composed of individual components that I can calculate for. So if I had multiple tubes in the system, I would basically go with different radii. I would go the tube by tube, and also every connection will have friction losses associated. So any kind of elbows will have friction losses associated with them as well. So that's what gets into this soup of data. So this is the working equation. Okay. I look at the velocity differences between outlet and inlet, as well as the difference in potential, because they might be at different elevations. And I integrate the difference in the 1 over density also between those 2 points. And this is the work of the moving parts minus, and this is sum up over all of these pieces of my system that might be tubes and elbows and so forth. Okay. So for all of them, these are the tabulated values, and I have some idea on the average velocity. Okay. All right, so now I'm gonna actually work on a problem. My system was rebooted before I came to class, so hopefully it's gonna cooperate here. No. Yes or no. Oh. All right. Okay. So just to let's see. Okay. So just to review quickly. So we have and by this is essentially interconversion of kinetic energy, potential energy, and enthalpy. Is equal to work done on fluid by moving parts minus irreversible friction losses. And this term is basically the total term divided by W. So this is a steady state balance. So at steady state, my W rho Vs is constant, so I can divide by it, right?
And the third term, is it dP or d rho?
D rho. D rho. 1 over rho d rho. By now you should be an expert in figuring out how I write rho or... It's been a couple of months.
And the slide was dP, so that's why I asked.
Hmm?
And the slides?
It is.
Yeah, the slide was
It should be d rho. Oh, just a second. It differs. dP d rho. dP. Oh, I don't have that. Okay. And then we have EV.
Is the delta for all left term or just for delta?
It is delta is for this because here I have integral already. Sorry. Right? So integral takes care of that. That's delta in there. Okay, so my EV is typically estimated as 1/2 average of the velocity square times a friction factor or loss factor. And this friction loss factor is some function of Reynolds number and shape. And it's typically tabulated in some shape or form. So one example for straight tube, EV is length of the tube divided by hydraulic radius times friction factor. And friction factor we're familiar with. And we can estimate as a function of Reynolds number, right? So what this becomes, I'm going to put this as star. Star becomes this Vm minus sum over all of the straight sections. So this done for each straight section. And then sum over all of the other parts. So these are valves, elbows, and so forth. And for those, I go to find EV in tables. So one such table is BSL table 751. So my velocity V is either the average velocity for the straight part or downstream velocity for some sort of fitting or valve. And the rest I should be able to estimate based on the tube geometries. So let's actually do an example. This is example 751. So we have the following system. There is So this is my plane 1. This is my plane 2. This is a pump. And these here are elbows. Okay. And then I need length, so this is 5 inches. This here is 300. This is not to scale because this is 100. This is 20. And this here is 120. Relatively simple system, the way systems go. And question is, what is the power output required to pump steady state water in this system? Power output to pump steady state water in the system, and at the rate Q is 12 cubic feet per minute. This is a typical question. Put together a system. What do I need to pump it? And here are the parameters. So parameters are mu is 1 centipoise, so I'm pumping water. Rho is, are you ready? 62.4 pounds mass per feet cube. Personally, I hate these units, but oh well. It's like, seriously, SI system was adopted in 70s. If I recall correctly. Internal pipe diameter is 4 inches, or 1/3 foot, just in case we didn't want to convert and stay in feet. And pressure at both plane 1 and 2 is atmospheric pressure. What is the total difference in elevation? It's 5 plus 100 minus 20. So how do I estimate flow regime here? That's my first step 1.
You can compute an average velocity.
I can, indeed. So my average velocity is this required flow rate divided by r squared b. and I have diameter, right? So it's 12 feet cubed per 60 seconds divided by 1/6 foot. (2.3 feet per second. Well, that's pretty fast. So my Reynolds number, I'm going to stay in feet. So that I don't have to convert everything else. Though my first impulse is, whenever I get units like this, is just to convert everything to SI units and go from there. So 1/3 times 2.3 times 62.4 divided by, and there's a conversion factor, by the way, that you can find for mu, and that conversion factor is 6.72 times 10 to the minus 4. So I got this for centipoise to pounds mass per feet times second. And believe it or not, all of those tables are in BSL. Well, so this is something over 10 to the 4, so it's turbulent. And given the size of the pipes, it wasn't even a question of whether it's turbulent, but just how turbulent. Okay, how bad is it? All right. And I need the Reynolds number in order to get the friction factor. So that's what I mean by how turbulent. All right, so let's now compute. Oh, well, we'll compute next time. It's half a page left.